Hello, welcome. My name is Hasan Ozkaynak from Beykent University, Istanbul, Turkey. I have been specializing in earthquake engineering and the effects of the earthquake that has been reflected to the structures, especially reinforced concrete structures. I have finished my PhD study 5 years ago by application of series of experimental studies. So I have lots of things to tell about the effects of earthquake in this lecture. The name of the topic of our lecture is the earthquake behavior of infilled reinforced concrete frames, which is commonly used in our country. In Turkey, there are too many structures that can be seen by the application of infill walls in using the participation way. Now let's us start the topics of the presentation. It will be composed of the statement of problem, the rationale of the study, and the literature review. The statement of the problem is actually this building. This building is very, very common in our country and in our neighborhood countries like in Macedonia, in Bulgaria, and there's those parts of the countries. These infill walls are mostly commonly used partitioning elements. Actually, in 1980s and 1990s, the application of reinforced concrete and concrete quality is very low in our country. In this stage, the general behavior of the reinforced concrete is very, very brittle. You cannot assume the structure to be ductile. We will talk on what is brittle, what is ductile, but I would like to say that this building is a vulnerable building. Vulnerable building means that it can take earthquake damage to itself because it has a rigidity, but it has displacement demands, too much displacement demands. During the earthquake, it makes the displacement, but the structure itself is brittle, so there are very big and very high damages on the structures. This kind of a structure is, we cannot say it's a reinforced concrete, it's a composite like infill wall and the reinforced concrete together, they work together. Actually, this is an unknown building and it's vulnerable to earthquake damages. This is our problem. Yes. Now, what is the significance of our research is to solve this problem, to strengthen the building that I showed one slide ago in the case of earthquake loads. Hollow brick infill walls are generally used as partitioning in most of the vulnerable low and mid-rise RC structures. Hollow brick infill walls and integrating them to the surrounding frame may improve the seismic capacity of the existing seismically deficient RC frame structures. Yes, the one that I showed you is seismically deficient building, and it gets earthquake damages to itself. What we will do is to integrate the infill wall to the RC structure. Integrating means like packaging the infill wall inside the RC frame. How it's gonna be packaged? We have some innovative products or innovative materials that I will present in this lesson. These elements can combine the infill wall to the surrounding RC frame. When you look to the structure, if there is a torsional deficiency of the structure and can torsionally behave very weak, it is the infill walls cannot stand in their own plane. so it works out of plane. To prevent this failure, we must integrate these infill walls, and we can use these infill walls as a fuse elements. What I mean is that when you integrate the infill wall to the RC structure, the RC elements have some damages, but together the infill wall has damages. When we compose them together, they work like a shear wall. So they are they behave well during the earthquake. This structure is the main structure that we will be interested in, and we will propose a strengthening method for this structure. The strengthening method includes some application of carbon fiber polymer sheets. Carbon fiber reinforced polymers has proven by many academical studies to be an efficient material for strengthening of reinforced concrete structures due to its low weight, it's easy to apply, and non-corrosiveness with high strength. This material is actually like a cotton, but it has very strength, yielding strength, much more strength than a reinforcement. But you have to apply this with an epoxy. You can see the CFRP, let's say it's a carbon fiber polymer. We need to apply this sheet element to the structure by using the epoxy that can be seen here. The epoxy is very high compressive strength. It's like a paint, but actually it's very easy to apply. First of all, you clean the surface of the structure. Then you first apply the epoxy like a paint to the mortar of the walls. After that, just after a second, we cannot wait too much for the application because it is getting hardened in a second. So you have to be very quickly when applying this CFRP. Directly you apply the CFRP, and last one you apply one more epoxy layer, and it's finished. We can understand how it's going to be applied in the structures in our next lectures. The questions are: define the vulnerable structure. What is epoxy? What is CFRP? The next argument is the rationale. The rationale of the study is actually based on this building. This building is the one that we have found from the literature that didn't take any serious damages in its very big diagonal crackings through the structures. This picture shows us that the infills have many effects and many good points to increase the strength and stiffness and the energy dissipation capacity of the structure. And we start from this picture. This picture shows us and tells us too many things, how we are going to integrate the infill walls to the RC structure. The rationale of this study is to increase the effectiveness of the CFRP-based retrofitting technique so that intact infill walls of vulnerable mid-rise RC buildings are transformed into a lateral load-resisting system. The CFRP makes the structure to behave like a shear wall to increase its stiffness, strength, and also, besides these two important properties, also increases the damping of the structure. When the damping of the structure increases, the energy dissipation capacity during the earthquake increases too much. This point is very, very important in the literature because the existing structures assume to have about 5% damping. But actually, in the case of the infill walls, when you integrate them, the infill walls to the structure by applying this CFRP, it increases too much, at least 2 times than 5%. We can say it's 10% and 15%. This 10% values means that the responsibility of the RC elements decreases tremendously, and the energy dissipation of the structure increases exponentially. What we have done is that we have performed several experiments during this study. This picture is a general photo taken from our laboratory in Istanbul Technical University. A series of pseudodynamic tests and quasi-static tests were performed in order to understand the general behavior of the infill walls when they are integrated to the reinforced concrete infill walls. We have understand that in this lecture, I think it will be better to understand what the academicians have proven up to now and what we can do after this point. We well know that the current studies up to now has been performed in experimental studies and theoretical studies. They mention and they highlight mostly that the infill walls, when they are integrated to the structures, increase the strength and stiffness of the structure. But what we have to do is to look this point of issue from another view, that the energy dissipation capacity of a structure. What we want to do is understanding the damping concept, because there are 3 important properties when they when they increase the earthquake performance of the structure: stiffness, strength, and damping. What is damping then? The transfer of mechanical energy to thermodynamic. Damping energy is the most important factor that highlights the damping coefficient of the structure. There are 2 main methods to identify the damping coefficient of the structure or structural components. The first one is the logarithmic decrement method. The second one, the energy loss method. The logarithmic decrement method requires a hammer test, as we see in this picture. In this picture, we can see a beam, a small beam, and it may be made up of reinforced concrete, or it may be made up of general steel or wood. It's not problem, but the methodology is same for all the structures or structural components. One hammer test means that a hammer is coming out and instantly pushing on the beam and getting the response, as we can see in this graphic. This graphic means that this part is the displacement demand of the structure or structural components versus time. At first, there is a big displacement, very big displacement, and after the time passes, the displacement amplitude decreases in a logarithmic way. And the backbones of these peak values are calculated in a very commonly known formula. You can determine the damping properties of the structures or structural components. But I want to emphasize that the damping coefficient that is determined from this graphic is just only the inherent damping. The inherent damping means that the damping of the structure in very elastic part of the movement, of the motion. This means that there is no damage in the structure. If there is no damage, there is some amount of damping, but if there is damage, the damping property increases. But this method is based on the elastic method. The other one is the energy loss method. It is commonly said as Jacobsen method. It was first identified in 1960s or 70s. The methods requires that you apply a structure, a beam or a column, a cyclic load, displacement-based cyclic load, and you receive this graphic. The longitudinal part is the restoring force and the deformation. This is one loop, hysteresis, force versus displacement. You calculate the area of the whole loop, and we can say that this is ED. And also, we need to calculate this triangle area, and let's say here E sub S0 here. And Kısa equivalent means that the equivalent energy is determined by using this formula. The main difference between the logarithmic decrement method and Jakobsen method is that the Jakobsen method is based on nonlinear properties. I mean that the structure can have some nonlinear damages, and we can understand the damping property after yielding point. The previous one, the logarithmic method, there is no damage. It's only in the elastic part. Let's look at the past studies to identify and to verify our experimental findings and to understand the experimental or analytical findings of the previous studies. Carneiro performed one study. This is actually a beam, very simple beam, and there are different reinforcement configurations here. The reinforcement configurations increases by number and by its diameter, and they perform cyclic tests on this RC reinforced concrete beam. They determined that the displacement in time, a sinusoidal type displacement. This can be applied by a pseudo dynamic testing method, which I will also be presenting in our lecture, the difference of the quasi-static test between the pseudo dynamic test. The main important point is that the structural component has displacement demands in plus and minus. So we can understand the cyclic behavior of the structure. When we derive the cyclic behavior, force versus displacement, it is very easy to apply this equation to the applied experiments. And this one was the first experimental study that we have seen in the literature, that we found out that when there is an increase in the concrete strength, the damping coefficient decreases, and when the reinforcement density increases, there is an highly increase in the damping ratio of the reinforced concrete sections. This study helped us to find out how we are going to quantify the damping properties of the structure. Then, according to this, I think it is possible for you to answer these questions. What is the damping of the structure? Define the two methods determining damping of the structure. What is the main role of infill walls? The last part of our presentation is have a better look to the literature review. In our country, this study was performed in 1998 by Professor Yüksel. His PhD study is mainly based on integration of the partitioning walls to the RC structure. They think about integrating the infill walls to the RC frame by making the casting together with the infill walls. You can imagine that there is a casting in the edge of the column or beam, but inside there is no casting. You put the concrete inside the in situ, and the concrete goes inside to the infill walls. When the concrete goes inside to the infill walls, they act together. The experimental finding of Professor Yüksel is based on these three main graphics. Actually, the red one belongs to the bare frame. The blue one belongs to the infill wall system, and the green one belongs to the integrated wall. We can see here that when we compare the behavior of the force displacement relation of the bare frame and the infill wall, there's a highly increase in strength and also the stiffness of the structure. The infill wall, there is no actually torsional effects. The only motion is in its own plane, so there is no sudden decrease in the forces. There is a good ductility of the structure when making it in infill wall. But when you change the construction style, like integrating the infill wall, I mean making the casting together and the concrete goes inside the infill brick elements, the strength increases very high from when you compare with the bare one. And also the stiffness of the structure increases very high. This study is we can say that this study is a milestone study of our researchers that can show us when you are successful enough to integrate the infill walls to the RC structure, the RC structure performance of the earthquake of RC structure may increase tremendously. 3 years after that study, the CFRP application comes out. There is no integration. The integration is based on only applying the CFRP cotton to the structure. This is 1/2 scale structure, maybe 3/4 scale. Actually, the method is to integrate the infill wall by applying the CFRP sheets, but this one is applied in diagonal bracing, like an X-type bracing. And the concentrated loads are in between the joints of the structure, the foundation of the structure, to integrate the infill wall and to make the CFRP successful enough to work together with the infill wall. You need to put these kinds of square extra CFRP sheets on the frame. This experiment has been performed monotonic tests. Monotonic test means in one direction, but plus and minus goes to the target displacement, comes to 0. Goes to the another target displacement and comes to the 0. And when we look at the backbone of the cyclic experiments here, this one is the black one is the one with the CFRP application. The red one is there is no CFRP application, and the green one is actually the bare frame. There is no infill, in fact, inside the RC frame. So we can see here that the strength and stiffness of the structure increases tremendously when you apply the CFRP and when you are successful enough to integrate the infill walls to the RC structure. After these two milestone studies, actually there are too many studies. The most important maybe for us is the one that were performed by Mosallam in 2006 and 2007. Because the one that I try to explain in this lecture is the energy dissipation capacity and the damping properties of the structure is mainly highlighted in these two milestone studies. Let's look at the study of the Negro. The displacement demands were received, and stiffness of the structure and the strength of the structure was highly understood after the application of experimental studies. This study was performed in Italy, and this is based on pseudodynamic tests. It's 1/1 scaled infill RC frame performed in laboratory of ELSA. Another study is coming from Gajewski, performed in Macedonia. It's the real shake table test. This shake table test could help to understand the effect of CFRP. As you see that there is a out of plane of the infill wall, but in the other photo, the infill walls are successful enough to stand in their own plane during the earthquake. The other study is the pseudodynamic study of Musala. Actually, this is there's an infill wall inside the steel frame. These are steel frames. It's actually it's not directly representing our case, but have an idea. To have an idea, it may be an important study for us to explain of our experimental studies. But the most important point of this study is to quantify the energy terms. The energy discretization was performed because in the study there were pseudodynamic tests. Pseudodynamic tests require an input of earthquake record. This earthquake record could supply us to understand the velocity, displacement, and the acceleration of the structure, and we can pass truly to the energy terms of the structure. The hysteretic energy and the damping energy can be quantified by this method. The shake table tests performed by Musala was to understand the damping coefficients of the structure. The damping coefficients were increased in the increasing levels of experiments. The increasing levels resulted with nonlinear behavior, resulted with high damages on the structure. So when the damage increased, the damping increased proportionally. Actually, there is no direct linear proportion, but when you see that when you make a general comparison, there's an increase in the damping property of the structure. Yes, this one we can watch the video here. The reinforced concrete infill wall was tested under shake table test in the effect of Düzce earthquake, and the RC structure could stand in its own plane and increase the earthquake performance of the structure. Well, the other studies performed by the application of CFRP in different way, in longitudinal way, because when the aspect ratio of the infill wall, the ratio between the length and the height of the infill wall changes, you need to apply the CFRP in different way. So when this ratio is much more greater than 1, you need to apply the CFRP in longitudinal direction. When this aspect ratio comes around 1.0, you need to change the application of CFRP in different way. This is the application of the one that proves the effect of CFRP material. Actually, this study is based on the GFRP, not carbon based. It was glass fiber, and when there is a comparison here, the lateral load versus lateral displacement. the increase of strength and stiffness can be highly seen. The other study is performed by Altun in different thickness of the band of the CFRP material. Actually, when you want to make the analytical solutions for the infill walls, you can model the infill walls like diagonal struts. So accordingly, when you apply the CFRP, you can change the thickness of the diagonal braces. If you want to increase the strength of the diagonal braces, you can increase the width of the CFRP. It means that directly increases the general behavior of the structure. This is the main idea to understand the thickness and the strength of the diagonal braces. In this case, when the width of the CFRP strips increases, the general behavior of the structure increases in stiffness and in strength. They were performed in 3 different widths, like 200 millimeter, 300 millimeter, and 400 millimeter. For the mock-up tests performed in Santa Marina, they performed an cyclic tests, which were firstly performed compression and tension. When first apply compression, you push the specimen to a target point, and when you get it to the tension position, you receive a hysteresis. I mean a regular force displacement relation, which helps us to understand the damping coefficient of the structure or structural components. What I mean is that the application of the CFRP material is very important. It changes according to the type of the infill wall and the dimensions of the infill wall. So to understand the effect of the CFRP material, you need to understand if it is placed in longitudinal way, how it behaves, and you when you place the CFRP material only in one direction or 2 direction, like this, like X type in diagonal type, and when you apply this in 2 phases, not only one phase. So in this study, they performed first monotonic, and in this part they performed first of all compression. When you put the loading in this way, this strut tries to work as their tension. So the tension and the compression struts changes accordingly to the directions of the infill wall. This supplies us to give a hysteresis relation and to understand the energy dissipation capacity of the structural components. The main outcome of the study is to understand the equivalent damping by applying Jacobsen method, not logarithmic decrement method, but Jacobsen method. What Jacobsen method told us that the energy dissipation in whole cycle, in one cycle, and the ratio, the energy dissipation in the first triangle area. When we divide these 2 terms together, and when you calculate this, we can determine an equivalent damping. Equivalent damping shows us the general damping, inherent damping plus the damping that is derived from the damages of the structure or structural component. When there is a damage or cracking or spoiling or crashing of the cover concrete monster, there is a high damage. This damage gives the infill walls extra friction, extra damping. What I told in the beginning of the lesson, that the damping is the energy that acts like thermodynamic, and when there is a friction, this friction is the main cause, main starting point of the damping When the damages increases, also the damping coefficient increases in similar way. In this study, when there is an increase in the load bearing capacity of the specimens, the equivalent damping coefficients decrease. It actually means that when there is a less damage in the mock-ups, in the wallets, we say the 1 meter to 1 meter walls as mock-ups or mock-ups or wallets. When they have less damage, proportionally they have less damping. This shows us when they increase the load bearing capacity, it means that there is a stiff specimen. The strengthening technique helped the mock-up to increase its stiffness and strength, so they remain in the elastic part, so there is no damage. When there is actually less damage, you can receive less damping. And when you go in 50 kips, like load bearing capacity, you determine about 20% of damping. And when you go to 200 kips in load bearing capacity, you receive about 7 or 6% damping capacity. This graphic is very important for us to understand that the damping is the damage actually is the source of damping. When the damage increase, damping coefficient and damping properties of the infill walls increases. This is the rationale of the study, and this is the most important starting point of our study. In this lecture, we performed some important lessons, lectures about the damping and the energy dissipation capacity. And in our next lectures, we will be presenting the damping properties of the infill walls and the CFRP-based retrofitting, how they affect the general energy dissipation capacity of the structure. Now, after all this lecture, I think it will be easy for you to answer these questions. What is the difference between shake table test and pseudo-dynamic tests? What is the effect of CFRP in the literature? What is the stiffness of the structure? Yes, this is the end of our lecture. If you have any question, please refer to the internet through the faculty. I'll appreciate for your attention. See you in next lecture. Thank you and goodbye.